Okay, so with enzyme catalyzed reactions, the amount of the catalyzed reaction will be dependent upon the amount of enzyme, obviously. We can pretty much just ignore the uncatalyzed reaction because it's going to be so much slower. I mean, if it was fast on its own, you wouldn't need a catalyst, would you? Right? You only need to catalyze things that are normally happen slowly. So, like I said before, the catalyzed reaction will take place at the active site. This is the place where the reactants bind the enzyme and then are transformed into products. So let's imagine a very simple reaction. We have an enzyme binding substrate, forming the enzyme substrate complex, and then it's going to be converted to product and released. We could actually come up with enzyme product goes to enzyme plus product and have another K3 and K minus 3, but we're trying to keep things as simple as possible, okay? So we imagine that the reaction goes like this, okay? And we can make it even simpler if we confine our analysis to the initial rate when there's no product. That is, you mix enzyme and substrate together. In the beginning, there is no product, so concentration of product is 0, which means enzyme plus product going back to substrate is going to be 0 because the product concentration is 0. That allows us to define the rate of formation of the enzyme substrate complex. Okay, there's only one way to form it now because you can't go backwards from enzyme plus product. Sorry. And that's going to be K1 times E times S. That's the forward rate. Once you've formed enzyme substrate complex, there are two ways to get rid of it. One is to go back to enzyme plus substrate, and the other one is to form product. So let's start with the simplified version here. So now the K minus 2 is pretty much 0. Well, it's there, but this reverse rate is going to be essentially 0. Okay, so the rate of formation of the enzyme substrate complex is K1 times E times S, and the rate of disappearance is two first order rates, K minus 1 times ES and K2 times ES. So K minus 1 is just dissociation, K2 is catalysis to form product. At the steady state, these two rates will be equivalent. That is, the enzyme substrate complex is constant. So if we set these two to be equal, then we get this relationship here. Enzyme times substrate over enzyme substrate complex is this ratio of intrinsic rate constants, and we're going to define that as the Km, the Michaelis constant. You notice it looks like an equilibrium constant of forming the enzyme substrate complex, right? It looks like an association constant. That is, where it looks like a dissociation constant, where enzyme substrate is going to enzyme plus free substrate. But as you'll see, appearances can be deceptive. It behaves that way, but it's not what the dissociation constant is. All right, so what we're looking at is this regime here, where it's the initial rate, but not the very first, maybe second or less. We want the point where the enzyme substrate complex is pretty much constant. So it's going to be formed early on, and now we're at the steady state approximation where the product is being formed and the substrate is dropping. Now, if you go too far out, the product will accumulate and the reverse rate becomes non-negligible. And so the rate of disappearance of product will slow down, the rate of appearance of product slows down, the rate of disappearance of substrate slows down. So we don't want to go too far in the reaction. In fact, this probably is too far. It depends on the rate constants. But usually we want to look at this early part here, but not too early. We want to look at the part where the enzyme substrate complex is constant. That is, this is true here, okay? And there's not too much product accumulated. So let's talk about the velocity of the reaction. That's going to be this K2 times enzyme substrate complex, right? The maximal velocity is where all of the enzyme is bound to substrate. So enzyme substrate complex is the same as the total enzyme concentration. There's really only two forms of the enzyme, free and bound to substrate, right? So Vmax is going to be K2 times E total. And E total is just the two forms of the enzyme added together, enzyme substrate complex plus free enzyme, okay? So V is K2 times ES, and Vmax is enzyme total, K2 times enzyme total, okay? So we can substitute all these things in. The K2s cancel out, and it's just enzyme substrate complex over enzyme total. It's an enzyme substrate complex over enzyme substrate complex plus free enzyme. All right, so we're going to, we have now determined that ES equals E times S over Km. Just rewriting this here, okay? So V over V max is ES over ES plus E. So E times S over Km over that, again, E times S over Km plus E. Hopefully you realize E's are going to cancel out now. I'm going to basically multiply both sides, both the top and the bottom rather, by Km over E, so all the E's will cancel out. If I multiply by Km over E, I'm going to have S on top left over, and on the bottom I'm going to have S as well, and plus Km. So this is what I end up with, S over S plus Km. And that's the Michaelis-Menten equation. V over V max equals S over Km plus S, or S, yeah. Okay. Notice that when the substrate concentration equals the Km, the rate will be 1/2 the max. That is, you'll get Km over Km plus Km is 1/2. Notice how similar this is to the ligand binding equation? Yeah, that looks familiar. It should. So you get a hyperbolic curve, okay, where when the substrate concentration equals the Km, we're at 1/2 the maximal velocity. And as substrate concentration increases beyond that, we'll approach a maximal velocity, Vmax. That is, V over Vmax will be 1. So, yeah, there's a similarity. The fraction of the maximal velocity, okay, the actual velocity over maximal velocity is S over S plus Km. The fraction for, ligand binding is as a fraction of the maximal ligand you can bind, it's ligand over ligand plus Kd. Okay, so they're both hyperbolic curves, and they're half maximal when the concentration of the small molecule, either the ligand or substrate, is the same as Kd or Km. So ligand to Kd, substrate Km. So Km is for substrates what Kd is for ligands. Okay? Now,